Section 2.4, numerical approximation to first order differential equation with initial condition y of x sub 0 is equal to y sub 0. So these are IVB problem, initial value problem, first order. Sometimes it's kind of like impossible or even difficult to solve the differential equation analytically. Case in point, dy dx is equal to e to the power of negative x squared. When you separate the variables, there is no way to integrate this. Why? This is one of those functions called non-elementary function. What's the definition of non-elementary function? It doesn't have antiderivative. No matter what you do, which method you apply, not going to happen. So we need to approximate. So in real life, we use computers, of course, but the computers, based on some methodology with either mathematician have come up with. Many moons ago, the first method of approximation came up by Mr. Leonard Euler, Swiss mathematician. And because it was the very first type of algorithm to approximate the solution of differential equations were difficult to solve, so it's not that accurate. Later on, mathematicians, some other mathematicians came up with better way because of the technology and all that, but this is like the very first one. So let's see what Mr. Leonard has done so we can go from there. So the idea behind Euler's method is as follows. Pretend this is your exact solution, this guy. This is the curve of exact solution. Mr. Leonard, what he did was chose a point on the solution, where it coincided with the initial condition. So this, let's say it's initial condition, which is selected on the exact solution. This dark line or curve is the exact solution. So the initial condition is on the exact solution. Do you see it? Then what he did, he incremented the x values by the amount of h. So h is the increment of the x's. In other words, then he went to the next point, but not necessarily on the what? On the exact curve, because we don't know how this guy looks like. So we like to kind of find, mimic this and come up with something like it, and hoping and praying to God this approximation, so this would be the approximated curve, is as close as possible to the exact. Okay? So what happens is the very first point will be on the exact solution because it's on the curve, okay, on the solution curve. However, the second point and the subsequent values you choose, the points you select, they are not on the exact solution. Turns out these are the points on the solution curves. Remember what solution curves was, right? Solution curves are like, when you draw infinite many family of curves, okay, but not necessarily going through this point, because the minute you draw the curve which goes through this point, that curve is what? One of a kind. Remember, that was called particular solution. Anyways, so here's what we do. You kind of let x1 to be x0 plus h, so increment the very first value of x, which is given. So remember, this point is given by the amount of h, and that will tell you, and they will tell you what h is. So h is called increment of the x-axis of the x. Sometimes it's called step size. Okay. So now x1 is equal to x0 plus h. x2 is equal to x1 plus h, but x1 was x0 plus h, so you get x0 plus 2h. x3 is x0 plus 3h, And lo and behold, we have this general formula, which is x sub n plus 1 equals x sub 0 plus n times h. And n is a bunch of whole numbers like what? 0, 1, 2, 3, and so on and so forth. Keep in mind, if you connect this point, P1, which is our initial value, to P2, that would be the tangent line to the exact curve. However, from that point and onwards, these tangent lines are not tangent to the exact curve. They are tangent to the solution curves passing through these points. So every time you select a point, there's a solution curve. And what you're doing is you're drawing the tangent to those solution curves, not the exact solution. So we are hoping and praying to God, if you continue this iteration, repeat the process over and over, eventually if this guy is not too far from the exact curve, you will have a decent approximation for the exact value of the solution at that point. So what happens is at x0, y0, you write the equation of this tangent line. Remember, so you go y1 minus y0 equals this guy, f of x0, y0 times x1 minus x0. Keep in mind f of x0, y0, because this guy was equal to, what was it, dy dx. That's like evaluating dy dx at x0, y0, which is the slope of the tangent line. So that's like y minus y1 times m slope, which is the function of x and y, because that's what dy dx is equal to, times x minus x1. Remember from algebra classes, right? So I'm using this formula, y minus y1 equals m times x minus x1, except I have 2 points on the tangent line. So I'm using 2 points form, so there it is. So if I manipulate this for y1, so y1 comes up to what? Remember, x1 minus x0 is h. That's the difference between these two values of x. That's the increment of the x. So this is h. So eventually I come up with y1 is equal to y0 plus h times the slope, which is f of x0, y0. Now I'm going to find the equation of this line. But remember, this line is no longer tangent to the exact. The only line is tangent to the exact solution is the first one. Thereafter, these are not tangent to the exact solution. They are tangent to the solution curves passing through these points. Keep that in mind. So using these points now, P2 and P3, so I'm going to use that equation from algebra and write y2 minus y1 equals now f of what? x1, y1. Now I have to find the slope here at this point, x2 minus x1. But remember, x2 minus x1 is still h, because that's the amount of increment. Solving this equation for y2, I get what? y2 is equal to y1 plus h times what? F of the slope evaluated at what? x1, y1. So in general, so here is a general formula. We have y sub n plus 1 equals y sub n plus h times f of xn, yn. And n goes from what? Takes all whole numbers, like 0, 1, 2, 3, and so on and so forth. Like when n is 0, I get y1 equals y0 plus h times f of x0, y0, and that's how you find y1, okay? So with that in mind, let's try this problem. And remember, you don't do these by hand. You either use computers or some sort of technology to get this going. Nobody does it by hand. As a matter of fact, Mathematica does it very nicely. So So we may go over that in class. So given y prime is equal to y minus x and y sub 0 is equal to 1/2, which is 0.5, use Euler's method with h is equal to 0.1, so that's your step size. That's the amount of increment you what? Increase x by every time you go over to the next iteration, and to obtain what? An approximation for y sub 1. So what is y sub 1 is equal to? Okay, using what? Euler's approximation. Okay, keep in mind what's given and what are you trying to find. x0 is 0, correct? Here is x0. y0 is 1/2, that's your initial condition. That's why it's y sub 0 is equal to 1/2. So that means x0 is 0, y0 is 1/2. Slope of the tangent line is y minus x. This is your slope, f of xy at any given time or for any given point. But remember, when it comes to the first tangent line, that's tangent to the exact solution, you know, when you use the initial condition. But thereafter, those are not tangent lines to the exact solution. Those are like tangent lines to the solution curves passing through those points which you select, you know, by incrementing what? X by the amount of, in this case, 0.1. So here's the formula. Y sub n plus 1 is y sub n plus h times f of x n y n. But remember, f of x and y n is y sub n, x sub n, because remember, this is your f of xy. So f of x and y n, that means replace the x's with x n, y with y n, because you're going to do some iteration here. You're going to write a program, so it will what? Compute a value, take that value, and recompute it for the next point, and recompute it with the third point, and this saga continues till you tell the computer or program to halt the what? Process. So we know what? Y sub 0 is equal to 1/2. So that means x sub 0 is 0, y sub 0 is 1/2. So this is given. Excuse me. But based on that, I like to evaluate the next value, y1. So in this formula, if I replace n's with 0, I get y of 1 equals y of 0 times 0.1 times y of 0 minus x of 0. So in the general formula, replace the n with zeros so you can get this. But guess what? I know y of 0, I know x of 0, I know h. So when you substitute, you get 0.55. Okay, so this would be what? An approximation for y of 0.1. Okay, the next one is y of 2, which is an approximation for y 0.2. What is this guy approximately equal to? Remember, we're incrementing the x by 0.1. This time you go y2, so replace the n with 1 in the magic formula here. So you get what? y2 equals y1 plus 0.1 h times quantity y1 minus x1. But remember, you already know what y1 is, which is 0.55. And what is x1? Well, if x0 is 0, and you increment this by what? What was it? 0.1, you get 0.1. You increment it one more time, that means you add 0.1, you get 0.3. You add 0.1, you get 0.3, and this saga continues. So remember, because the step size was 0.1 and you started at 0, so every time you want to find the subsequent values of x, just simply add 0.1 to the previous value. So this time x1 is equal to 0.1. So that goes right here. Y1, we got it from here, 0.55. And when you work this out, you get 0.595. Remember, this is an approximation of the solution evaluated at 0.2. This would be an approximation for solution evaluated at 0.1. So what you do, you kind of make a table. Remember, nobody does this by hand. You kind of do it by computers. So you select the values of n, like 1 all the way through 10. Okay. The reason we stopped at 10, because x sub 10, if you keep incrementing x by 0.1, x sub 10 comes up to equal to 1. So therefore, we have to iterate this process 10 times. So we got to do a do loop or something like that. Tell the computer to what? Repeat the process 10 times so we can get to 1, because it says approximate y of 1. So the two values which I got previously, those are y of 0.1 and 0.2. So I need to go all the way to 10 in order to get myself to x equals 1. So when you do this 10 times, you get this. The question is, how does it compare to exact? Not that you have this available in real life, but let's say somehow by experiment or by past data, you had something to compare it with. So this is exact, this is approximation. Notice exact is 0.640859. We came up with what? Approximation of 0.70312. So the absolute error, which is what? You subtract what? The approximation from exact, take the absolute value, is this. Then you can find the error, like, find the absolute error divided by exact. That gives you relative error. And then if you multiply the relative error by 100%, that gives you percentage of relative error. So you can tell what percent kind of error do you have. So the question is, how do we improve this? Because notice it's not quite the same as this. One way is to decrease your step sizes. Instead of 0.1, take 0.05. Or instead of 0.05, take 0.005, and so on and so forth. So two factors improves this. Either you have to what? Decrease your step size or increase your what? N. So instead of 10, take like what? 20 steps. So decreasing the step size will improve the problem. As a matter of fact, if you take h is equal to 0.01, the approximation comes up to 0.68652. Notice we are kind of getting there, but we are not there yet. So that would be one of the things we could do. But remember, in real life, you can't just do things, because things cost money and time and resources. The minute you increase the number of iteration, that means what? Now you have to spend more money on the programming, and it will take time and effort to get the desired answer. So it's not cheap. In classroom setting, you can go, well, let's decrease the step size. But in real life, you're talking about money, because that requires time and extra resources, and you have to hire people to do the job. So it is not easy than saying it. Okay, so because that was the very first approximation Mr. Euler came up with, then there are other methods, which I have listed two of them, which is in the book, but these are not the only two ones. If you take a class in numerical analysis, there are other methods to approximate what? The solution of differential equation or any concept in mathematics. But the ones we are dealing with, one of them is called modified Euler's method, which is done by a German mathematician, Heinz method. So instead of taking the points on a tangent line, he uses the midpoint. The other one is done by, in this century, is done by two German mathematicians, Rang and Kata. So it's called Ranga-Kata method of order 4. So this would be Ranga-Kata of order 4. This is much more accurate than the previous methods. But then again, it's a very complicated programming, but it does the job. So just to get a feel for how accurate these three methods, Euler's, modified Euler, and Ranga-Kata method order 4 is, here is the accuracy of each method. In Euler's, the error is proportional to what? To the step size. Whatever the step size is, error is about equal to the step size, okay? For modified Euler methods, which is Heinz method, the error is proportional to the step size squared. Notice the error is becoming what? Smaller, okay? But in Ranga-Kata, notice the error is what? H to the power of 5, which is much smaller than this. So this guy, you know, if I would do this using Ranga-Kata method, instead of taking 10 steps to get something close to the exact, Ranga-Kata might give you this close to this answer in step 2 right away. It is that accurate. So speaking of the errors, you have two kinds of errors, local error and global error. Local is caused by one iteration, and global is caused by many iterations. So those are, then we have truncation error, then we have round off error. So there are too many factors which what influences the final answer. So this was just in a nutshell what this section is all about. But we will just stop here and not go over the other two methods. So Euler's method is the only approximation method which we will be responsible for. Thank you.